So my name is Alex Donze. I'm part of this small company called DECYPHIR, and I want to talk about monitoring cyber physical systems. All right. So this is a kind of classical slide about cyber physical systems. Like it's about everything. So cyber physical system, in case you don't know or not familiar with it, it's about anything that's computerized and has significant interaction with its environment. Okay, so you have computer systems that interacts with their environments. And so that goes from cars, and I'm going to talk a lot about cars, drones, robots, the Internet of Stuff, and medical devices. And okay, and one of the central questions there is well, can we use some sort of formal methods to improve the safety, reliability, and performance of these systems? All right. And why? Because, well, it's kind of safety critical. Like it's those things are more and more driving your cars. They will. They're driving your body, and believe me, there's a lot of issues in the devices that you put that can drive your heart, for example. So I won't elaborate on this. You can find data about software-related bugs that leads to safety problems. I think I don't need to convince you that this is an important issue. So, what's the fundamental issue when designing a cyber physical system? So again, this is about computerized systems that interacts with their environment. So you have basically two parts. So you really have the software that you're mostly familiar with, and then you have the world, which you are kind of familiar with, but not that. And you want those two things to interact, and the software, the main issue with a CPS is really that this software should really be aware of what's going on there. Whereas for most of other types of software, you can live in a closed environment, like you can only consider the other variables or the other things, and it's fine. But here you have this messy thing that's the world around you that you have to take into account. Okay, so that's really, and the world is complicated. Like, it's a triviality to say, but I mean, this kind of picture are there to illustrate how complicated the world is. And if you go into this is just the physical, like engineered world, but then you have biology too, and it's even more messy. Like it's very difficult, very complicated. We know nothing, really. We know, so we can model to some extent, but it's very complex. Now on the software side, it's kind of much easier, but it's getting more and more complex too. And I mean, I found this chart. I mean, just one chart to illustrate how complex this has become. And the interesting thing is that one thing I found interesting in there is that today the thing out there that has the highest number of line of code is a car. So if you have, it has more line of code than Facebook or operating systems or Boeings or different things, etc. So it's yeah, millions of code. Now, if you want to use formal methods to design those things reliably, in practice, what we see is that most industrial techniques are focused on the code. So the first, the thing we saw before, which actually means, so they want to verify the controller, so which means that they verify basically the embedded C code or whatever other type of code you have embedded there, and really this means testing this code. And in the course of this school, it can mean just monitoring the code. All right, and you have some formal methods that are marketed out there, but and that apply to this code. They do some static analysis. You can do some property proving, but mostly they don't scale to the closed loop system. What I mean closed loop system is really the software and this environment. If this is a chart of kind of analysis techniques that exist for CPS. And I mean, on one end, you have things that scales, on one axis. On the other axis, you have things that proves that is exhaustiveness. And at the bottom right there, you have theorem proving, which means that it's perfectly formal. And you're going to prove that everything is safe and so on. But it doesn't scale at all, like it's for small properties. And here you just have simulation, just trying the thing, and kind of try to see if it worked or not. You can do it with mostly everything, but you didn't prove anything. And now there's a whole landscape of different analysis techniques that tries to be more formal or more exhaustive. And I've put kind of runtime verification somewhere here in the middle, where it's still highly scalable because it's not so far from simulation and testing, and it becomes there is some formality in it, there is some formal aspects. Okay, and it's really, and I think you've seen or you're going to see that this term several times. It's some sort of lightweight verification technique. Okay, which improves on basic testing. And the thing it does for improving on automatic testing is it automates the assessment part. Like you do a test and then you get data and then you can say, automatically you say, well, it works, it satisfied the requirement, it satisfied the specification, etc. And this part, and it's a big thing to automate on, and on a rigorous way. Still, sometimes you will see the term semi-formal method. Semi in the sense that it's not complete, so you're not going to see. I mean, I mentioned it's not going to be exhaustive. And the formal part really comes from the rigorously defined requirements. And I've thrown in there a term, which is falsification, which is a variant of runtime verification, which the principle is that if you have something that can automate the assessment part, okay, then you can have an automatic technique that will generate test cases, generate scenarios, and checking if it's satisfied or not, and try to find just one scenario that will not satisfy the requirement. And if you cannot do that, and if you cannot falsify a requirement, then you kind of proved, or you have some confidence that the requirement is true. Okay, and this leads to this principle of, oh, what are those slides? Actually, I had moved this later anyway. This paradigm we're working into, which is the requirement-driven design, where really we start with the requirements, and then we do things, we try to create them, we check them, we mine them, and we test that on the controller in the plant. Okay, and so in our in our company we have a toolbox which is called Bridge, which tries to apply this in practice and implements some of these techniques. And at the center of it, we have something that deals with those requirements and can do test generation. And I mentioned you can do falsification, and then the kind of inverse of falsification, which is calibration, that you try to find a situation that better satisfy a requirement. Okay. So, and this is applied to something that's more and more applied also in the industry, which is model-based design, where so when you design a cyber physical systems, you start with some high-level abstraction of it, and then you test it and you design it, and then you go through different stages toward reality. That is, you start with models, and then you generate the software, then you test this with the hardware, then you do prototyping. And here, if not familiar with those terms, so MIL means model in the loop. So that's the most abstract stage. SEALs means software in the loop, where you generated the software that's going to run on your car, but then you just test it with a model. And then hardware in the loop, then you test your controller with some test bed, like you have some engine and you test it. And so, but during all these stages, you get to produce data to monitor. Okay, and this is what we're interested in. How do we analyze automatically this data to improve this model-based design process? So I wanted to organize kind of this talk into two parts, which, in lack of better terms, I call like traditional CPS and modern CPS. And in what I call traditional CPS is the things that have been around, and again I'll get into the automotive landscape. So things that have been around for years, and that is like powertrain control and kind of more newer things like electric drive, battery management systems. So when you have a car, like everything that controls your engine and that, which falls into the category of like classical control design. Okay, and in this context, there is like a well-established toolchain which is called Simulink mostly, and an established toolchain that goes from modeling to code generation to actually, yeah, to embedded code. And in this part, what we monitor, when we're going to talk about monitoring signals, that is time series, which is basically the picture we had before. Those things on the right, okay? And I wanted to talk about more modern CPS, and what I call modern CPS is all those nasty things that they do now with machine learning-based perception and like multiple sensors, and that they want to do for ADAS. So ADAS is an advanced driving assistance system, and that goes to autonomous driving. And in that context, it's a mess still. You have onboard PC with high-end GPU for deep neural network, and there is no established toolchain. And what those things try to do is they look at the world around, and really, what you're monitoring here is the world. Like it's, and what can we do with that? So it's less mature part. So it's more of a start of experimenting this second part. But I mean, you'll see. I just want to start a conversation. Yeah, please stop me any time you want to before I go into the first part. All right. So right now, or not so long ago, how people do check high-level design specifications. Okay, so. And again, I'm in the context of some automotive system that you're designing, and you have an engineer, some engineer that knows, that has experience and knows how the engine should behave, how such or such component should behave, and he or she will have something she wants to check on the motor, and she will say, okay, let's check the transient response of X when you drive on a highway on 101 and the temperature is around 40 degrees. It's really like that. And so you get something in natural language and get in some specs, and sometimes they write it down, sometimes they don't. Give that to the control designer. So control designer then just do his things and do some simulations or collecting data, as I mentioned, and then see that's what they get. And that, for her, this doesn't look right. Now this one, maybe see. Well, it's maybe should be okay. And then she looks at the last one, and yeah, oh, this one is good. Okay, so that's kind of the current process, or I mean, it's still going on in lots of places. So the question, I mean, the question is, can we improve this this process? And to improve on this process, what we would like to do is be able to formalize what does it mean to say, hoo-hoo, well, should be okay, looks good, oh, it's weird, clearly wrong, fuzzy. How can we do something more formal than that? And yeah, now getting to temporal logic. So temporal logic is, I think, I guess most of you are familiar with, but correct me if I'm wrong. Am I wrong? I don't look wrong. Anyway, so temporal logic specify properties over time. Next 3 days, the highest temperature is going to be 75 degrees. In the west, it's going to be above 60 degrees. That's a Californian statement. So it's Fahrenheit and mild temperatures. And so, as you know, you have propositions, which the highest temperature will be below 75 degrees, lowest will be above 60 degrees. So you can say T smaller than 75, T greater than 60, and you have propositional logic, proposition connected by Boolean operators. All right. Now, oops. Okay, that's it. So now LTL is, I mean, the simplest temporal logic where you take these propositions and you add temporal operator. So A is true now, A is true in the next time step, in the next operator. Eventually, A will be true in the future. Globally, A will be globally always true in the future. And until so A will hold true until B becomes true, right? So now, if we want to go back to our example and say for the next 3 days, the temperature will be below blah, blah, blah. If LTL using a representation of the state t smaller than 75 and t greater than 60 for A, you'll have to say XA and XXA and XXXA for the next 3 days. Okay, so STL, very simply stated, is an extension of LTL that gives you interval time operators to specify times periods where the proposition or subformulas are going to be true. So, I mean, technically, LTL is to me it's really so this timing operator, like this time intervals, and the fact that you operate on real valued signals. Okay, and so if you go into an example, so you say always between 0 and 3, t of t, in those bounds, and then you have the signal, the corresponding signal that will satisfy this property. This is the one bounded by those two things, so it's very simple. Now, if you want to say that your signal is going to stabilize at some point, so you say eventually, maybe between 20 and 60, it will always be the case that in absolute value x is going to be smaller than 0, 1. And that corresponds to these types of signals. So you start somewhere outside your nice region, and before 60 seconds, you will get into this region and you stay there for, I think, at least, no, it's always until the end of the trace. Okay. So now what's interesting about this logic, the second thing that's interesting about this logic is that it comes equipped with quantitative semantics, so that you don't only say that a trace satisfies a formula, but you can say by how much you can satisfy it. So for a given trace and a formula, you can map phi and x to some value, and intuitively this value is the sign distance from the trace to the set of traces that do not satisfy it. Okay, so if you have your signal here, and this is the bad region for your signal, then the quantitative satisfaction is going to give you this distance between your signal and that. And if it goes into the bad region, is going to give you the distance from the signal to the outside of the bad region. Right. So, so if we come back to this this question, can we formalize those UHO or should be okay or looks good or weird or clearly wrong? So this quantitative semantics is a tool that allows you to quantify the quality of the different assessment, and so that can help you map those assessments to some number, some formal number that's machine actionable. Okay. So, yeah. Okay, and I had copied. Yeah, and I have shown these slides already. But what's okay? I want. Yeah. So, and that's this this quantitative semantics. I mean, this logic and quantitative semantics is what will enable the falsification part to be done more efficiently. And let me tell you a little bit more about this. So falsification again is about finding finding a trace, finding a behavior that do not satisfy a requirement. So you have a model. You have a model. You can give this model some input, and this input produces some output. So the question is to find which input is going to violate the requirements you're looking at. Okay. And so the goal is to design this falsification engine that will collect the output of the system, do something, create a new input, send it, analyze it, etc., until something is found. That's the generic procedure. And the way it works is it uses this robustness, which is the quantitative semantics, and it gives that to some optimization engine, and which will try to actively minimize this robustness. Okay, so it will try to find a way to go toward regions where this quantitative semantics is low, and if this low go below 0, then you found something that violates the specification. And I'm voluntarily vague about what kind of optimization you can use there. So because what I'm trying to build is something where I'm trying to build a framework of this more than the actual implementation. So I'm trying to build something that's modular, where really the added value of the framework is to, once you have a model and you have a formula, then it knows how to compute the robustness, of course, so the monitoring part. And then it packs all this into a standard kind of optimization problem. And then that's the job of someone else to design the best optimization engine to do this. But I do the interface. So basically what I'm saying is that we can transform this this model plus formula into some optimization problem that somebody then generate, on which you can try different types of engines. So of course we have different engines. I don't want to go into the detail of that here, but yes. Yeah. It uses the data of the model. Like it uses the, it uses the signals just the signals. Yeah. Okay. So, so you have the input generator, and also, we have something that helps the engineer design the flexible way, the types of inputs. The input generator. Actually, there's a slide just after that. So yeah, we have different families of input generation thing, and basically it all comes down to some parameterization. Okay, so in the end, what you have is you have a parameter space, and the way you go from a parameter value in this parameter space to a signal, there are many ways to do that, and it's there you need some insight. I agree, you need some insight on the model, and it's best done with engineers that know the model, like that know what's relevant, what types of inputs you want to test. If you want to test the steps, or if you want to test like some sinusoids or some constant ramps. So you have different, you have different templates, like different patterns that you can try that are more relevant. So if you have no clue at all about the input space, then it makes the problem much more difficult. But you can still give that. I mean, in the end, well, you have an input space, you have a parameter space, and you get a cost function because from one parameter you go to an input, you go to a simulation, you go to a signal, you go to a robustness. You pack all this into one objective function, and it's completely the solver. You can give this to any optimization, black box optimization solver. You try some things, get a result. Try something else, it looks better. You know, you can design all sorts of stuff, even if it's still black box. But I agree that the input design is where you need the most insight into the model. Yeah, you could. But I personally would not claim that because I'm not an expert in automotive. I'm not the expert engineer. All right. So yeah, we applied this to some engine control and found something that was clearly not good. And yeah, and they were happy, and so now they're using more this technique. And today we there's a lot of work going on, and we try to apply this world framework. And the main application we have now is developing this next. The hydrogen fuel cell, a propelled car, engine control. Okay. I'm going probably to jump to the next part. So if you have more questions on this, maybe the time. So I had planned I had a plan for maybe some demo, but yeah, there was some computer problem. So maybe offline we'll do that. Yeah, this is not my computer there. Okay, so so this was the first part, where so what we have is a mostly signal like time series, and we developed this signal tempo logic, and it's getting kind of mature and applied. And last year, the last couple of years, we started thinking about what can be done is more modern or today's concerns, and what they try to develop, which is autonomous driving and advanced driving. So ADAS is advanced driving assistance system. Recall the term. And so we have this car. And again, it's a CPS, so you have a controller for the car and the environment. And now the environment that's analyzed, or that's that's analyzed by the car, is very complex. So it includes, I mean, the car has to be aware of really everything that's around it. And a lot of techniques that are developed now use vision systems. And they use some machine learning based perception algorithms. So you have this deep neural network thing there. So, and it's, as you can imagine, it's very hard to develop. And so the question is, that's very, that interests a lot of people today. Is what can be done there. But the first thing is, okay, that's a mess. And what are we looking at, and what can really be monitored there? What should be monitored? What should we look at? And so when we started looking at this problem, we kind of simplified this first and say, okay, let's look at a very simple scene where we'll just have this road and this car, and we'll modify a few we'll modify a few parameters. And this, again, I mean, this comes back to the previous questions and comments, which is how do we parameterize the input space? Like, what we, yeah, really, what are we looking at? And so the first, one of the first thing is that we did is doing this exercise of finding some parameterization of some scene, and we developed this this feature space where we said, okay, we have this simple background, this car, and we vary a few parameters. So the position of the car and the brightness here, and then we have this system that's able, this deep neural network that's able to recognize the scene and say whereas there is a car or not. If there is a car, of course there is a car in all those pictures, but sometimes not. And okay, formalizing is there a car or not? It's relatively simple in that case. So here the problem is really the input space. Once you've done that, you can still give that to some classification engine and try to find just as a kind of thought experiment. Try to find, a situation where something unusual happens. So, and like you don't see very well on this screen, but here, so basically you have the feature space, and so the three dimensions I mentioned, which is the brightness, and then the position of the car, and we just did some search, so basically stupid search in this parameter space where we tried all different variants of this image and monitored the result of the classification. And we found that, of course, when it's when it's very bright, so the system fails, which is expected. And when it's not, when the image is correct, is reasonable, it mostly succeeds. But you can still find in this region where the human eye tells you that it should be trivial to recognize the picture, you can find small bugs like this. And so this is a well-known issue with image recognition with vision systems, which is that even if the system seems very performant, that is, you have an image and it seems very good at recognizing stuff, you can find very small variations of pictures where that's for a human eye, nothing changes, but for the neural network, the classification fails. So on an image by image basis, then it's it's a well-known problem. So, and there is work. Of course, there is a lot of work around trying to robustify this classification problem, so that when you make a small, if your classification is correct and you make a small variation on it, then it remains correct. Yep. Exactly. I'm saying, yeah, I'm saying there's a lot of work on this. So, but we are interested in closing the loop. Thanks. It's good to see people following. So, but this is a hard problem already, but we want the harder one. All right. And it's okay. It's a hard problem, but a lot of people working on. And eventually, what matters is what matters really is what happens if we re-inject those systems into the world system, right? Because I mean, your system can fail to recognize an obstacle, but maybe it doesn't matter. Like it can fail if it fails for half a millisecond, then and succeeded right after, then it's still fine. So what's interesting is finding situations where scenarios where these failures are robust in some sense enough so that it's a danger for the safety of the whole system. Okay, so that's the kind of thing we wanted to the kind of thing we wanted to test in some sort of framework. But then we got into the problem that whereas for what I was calling traditional CPS, there is established toolchains where you can test system integration and things and go from modeling the whole system to the software code generation and so on. In this context of autonomous driving and this machine learning perception-based components, there is no established toolchain. So it's it was a bit more difficult. So we had to find a way to do something. And the main problem, one of the main problem is that now what we're considering are not only streams of numbers, data, we're considering streams of images. Okay, so we have signals, and it's a sequences of images, and you want to specify properties on that and test that. So actually we made a first attempt at generating images in Simulink. I don't know how many people are familiar with Simulink here, actually. Maybe not that many. But, okay, it's not a tool for that. It's not a tool for generating pictures and you are? Yeah. 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 So this it's not a question for me. It's a question for engineer, and that's they do they have to deal with that. That's for sure. Yeah, it's the same. I mean, it's a reverse. Like it's an issue. Both cases are issues in some situations. There are tons of weird situations that they have to deal with. I mean, it's just one example of one thing that can happen. So the question is not really how to deal with those issues one by one. The questions we wanted to answer here is how to build some sort of frameworks where an engineer can kind of specify what the problem is and detect it and find a solution for it. You see what I mean? And we're advocating this whole model-based testing framework where we can do repeatable simulations and specify properties and then make the thing run and detect that something is wrong. We need a framework. So that's what we wanted to try. But that's a good question. And really, what I'm talking about there is like some preliminary work in that direction. It's current investigations in academia as well as in industry. But I just wanted to relate about our own toying experiments in this. But I think I'm happy because the message kind of got in already, sort of. Yeah. Yeah. You can, yeah. If you, I mean, you can. The whole so my goal here is kind of keeping the same framework. So where we can do requirement mining and classification and stuff. The question is, what do we put in the different boxes in terms of input generation and instead of requirements? How do you plug this in? Okay. And so to plug this in, we had to have some way of having the images and the streams and the video in the loop in some sort of tool framework. And here I'm saying, so with something we found for this, so Simulink failed miserably. And there's a trend to use actually game engines. Yeah. Yeah. It's feels. I mean, okay. Simulink. Yeah. Simulink is not good at at treating frames, streams. Okay. Yeah. 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 You can. Okay. You can. Yeah. I mean, I'm a little bit harsh at Simulink, but okay, Simulink is not good at creating the visualization, but then if you have something that creates a visualization for it and collect the data, and then you can plug Simulink on it, and many people do that. They just do the controller, and Simulink just send numbers and gets numbers back. Okay, or what I'm saying is that if you try to make a Simulink model that will perform some sort of image analysis on it during simulation, it's it doesn't work. Like it's okay. It can work if you have a lot of horsepower, but very lot. It's not efficient, not at all. So I was playing with, literally playing, with another type of engine, which actually is also a hybrid dynamical system simulator, and it's called the Unity game engine. And we started with the Udacity. So maybe you know Udacity is this kind of MOOC online classes platform. And they have a self-driving class, nano degree, and they provide this open source simulator, which is kind of basic, but it got me to learn about this this Unity game engine. And the Unity game engine, so it's to create games. So you have in games you have levels, which are called scenes in the scene, and scenes are a collection of game objects. And I mean, I don't want to insist on the game aspect, I just on the objects. And each object has visual attributes, physics, scripts. And the engine is actually a hybrid system simulator, which at each time step will do the same thing as Simulink does, which is finding the next step, the next state of your systems based on each own scripts of each object. Okay, but the important thing an interesting thing is that it's optimized to render as many frames as possible per second. So it does this physics simulation, so the next state, but also it generates those images. Okay, so that's what makes it interesting for working with computer visions programs, because it will spit out as many frames as possible, and it will really be optimized for that. So yeah, just some small things. So coming back to this picture I showed, here you have the different scenes, and here you have a list of objects that are part of the game, including including the car, which is the main thing. And the interesting pane is there where you have here you can connect different scripts, which is in C#, actually, if you're interested. And you can attach scripts to those objects. And the even more interesting thing is that those scripts are parameterized, and you have an access to those parameters. So all these fields are things that you can tune and things. And there is some interface. So again, if you're coding in C#, you can play with those parameters. And so why I was interested in that is because this means that you can completely parameterize a scene, a scenario, and you can, this is my input generator now, okay? This is how I connect my parameters to some input generators that I give to my system. And now that I have my input generator and my parameters, I just need the other side, which is the property monitoring, right? The runtime verification part, and then I can give that to my falsifier, and I can do stuff. Okay, so just to go through some examples. If when you see this thing running, and here you can see it generating pictures. Actually, so it's running, and there was a button I clicked, and then it collected the frames, and that gave me a set a set of frames around the track. Okay. So yeah. All right. So now I wanted to make this more interesting, and I wanted to actually test something on that. So I designed. Okay, I had an obstacle on this road. So I parameterized my my scenario, and what I did is that I put some code in the middle there. And so you might wonder what I'm doing there. Right. So no. So the cow is just leading away. What I'm doing here is I'm collecting images. So the same set of images as previously, where every image has a cow in front of it, of the car. Okay. So I don't know if you can guess where I'm going there. All right. Yeah. So, and then with this, I could design an automatic co-avoidance system, an ACAS. Because with my set of cow no cow images, so we could train a neural network that could recognize features also all around the track. So I have images of all around the track where, so one set of images without cow, one set with cow, and I train a neural network to recognize from them. Okay. And then we implemented a simple system that would send braking commands whenever a cow is detected. So I have I have a simple controller that goes around the track, and on top of this, I had this ACAS thing. So now I could close the loop with this thing, where I have my tool, so our tool bridge, which was sending again scene parameters. So that would include different modifications of the scenes, like characteristics of the car, characteristic of the cow, and now those two, the Unity game engine, so the simulator was connected to my neural network, which is implemented in Python with TensorFlow, which is kind of usual. And this would send images. So during simulation, it sends images to to TensorFlow, which classifies the images with cow, no cow. And whereas when the cow is detected, it sends back a command saying, yeah, you have to brake. Okay. And so now this, what I'm doing mostly is offline monitoring. That's when the simulation is complete, I collect data here, and I send back the simulation trace to bridge that then analyze the result and look at different properties and stuff. Okay, so that's as far as we got in terms of having some sort of complete framework with neural network in the loop, and that does the whole system level kind of analysis. And so we did some experiments with this, and the first thing is we're looking at static scenes. That is static in the sense that the car doesn't move, and we just put the car in front of the cow, and we test different situations, different variations. And here, the variations that we test are just the orientation and the color of the cow. And yeah, we don't see the results very well. I think I have a better picture than that, but I mean you can still see kind of. So in this axis is the the orientation, and this axis is the color. And because so I told you I have two sets. I have a cow and no-cow images, but you might have noticed that the cow is always red. Right, so we thought, okay, what happens if the cow is not red? And well, if it's black, then the classification actually fails. But it's not so surprising that kind of more surprising thing is that there is a sensitivity also in this axis, which is the orientation of the curve. So on this particular image, you can see that some orientation works better than others. So it's not so surprising either, but still. And yeah. 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 So I was saying that instead of my ACAS, if I have a real system, how would I go testing it? Or yeah. So or are you saying how do I deploy my car detecting on a real car? So yeah. I mean, the current practice is like I wrote somewhere. You have basically PC and GPUs on board, so you can directly deploy my this neural network that detects cows. If it's useful, then you can deploy it on the same machine as this one or another one just on board, and then it will collect images from the cameras, and it will then be connected to the brakes of the actual car, and that's really how it's done now. Yeah. 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 No, it's not. Yeah. Oh yeah, I'm not saying this is. So, okay, I would not. Yeah. So that's a good question. So the images I used to train this algorithm are still. I mean, it's much nicer than what I was playing with when I was doing simulating, but it's still not really photorealistic. Okay. It's not that they're not good images. Now I would not use this one, and I don't know, but yeah, clearly they're not. This is clearly not good enough. Although I'm not sure how bad it is. Maybe not that bad, but you have to do a little bit better. But that's not my expertise either. So you would have to get a graphist. I mean, I really believe that you can still use the same type of framework and actually train a useful algorithm. But then you have to just improve on the photorealism of the images. So, and I mean, I think this game engine is, or you can have something better, and people are developing stuff better. But it could almost be used for this because it's a good engine to make photorealistic images and go over. But you see the route to implementation. I mean, you need to improve this image generation. And I don't know to what point you need to improve this to make it useful in practice. So you have to map. There is some work to do to see the difference. But okay, I don't know if I'm confusing you more than I'm answering your question. But I mean, the current practice is people, when they train neural network, they work on photos, videos, streams. They have huge database of their recordings. And they train the neural networks on those videos, so they are real images. The point I'm making here, and people are trying to make sometimes, is that no matter how big this data set is, there will be gaps in the trainings. There will be situations where the neural network was not trained properly, and we are kind of suggesting that there's a need to augment those data sets, to use some synthetic, to some extent, data to improve this training. Okay, and then also videos, and so it's not, you cannot do simulation with videos. You cannot recreate the scenarios. So you need some scenario, some simulator to make variation of scenario, everything. So, and not many people. I mean, I know Waymo at Google. They have these types of simulator and approach, but they're about the only company that has something quite advanced in that field. So it's still very. Yeah, lots of people are still only relying on images. Anyway, I could go on and on. Just closing the loop. I'm probably going to stop early, but anyway. So, so before I was just testing like static scenes. And now here I'm showing a situation where it matters. So I'm trying a simulation. So I identified that the black cow could be a problem, and I'm just verifying that. And here you could see that there was a collision. Here I'm just showing two simulations, one with the red cow and one with the black cow. And you don't see the difference color actually, but the second simulation was with the red cow. And what I'm showing here is that simulation is translating into a signal that I can analyze with the previous framework. And these signals here are just, for now, it's just the classification score. Okay, meaning that if it's 1, then the cow is detected. If it's 0, there's no cow detected. And what was interesting in those in this experiment is that in the case of the black cow, there was detection, but this detection happened like 1 second after, and it was it was too late for the algorithm to react, and this led to a collision. So in this third plot, here I have the position of the cow on the z-axis, and it's just showing that there is a small jump here, resulting from the collision. Like no cow was harmed in this experiment, of course. Yeah, so yeah, and that was to illustrate like this timing difference. This is where like the difference matter. Okay, so so I wanted to give a quick takeaway messages from there. So going back to traditional CPS, what we see is that there is an established tool chains that goes from models to code, and that where every steps you can do full system level integration and you can monitor everything. And in this context, so basically Simulink for the automotive industry, but there are others. Runtime verification is making its way. So the time is right. Now people can do those simulations and can correct and collect different data everywhere. And now it's time you can start making properties and integrating runtime verification in the design process. That's what's happening now. And of course, there is always more work to do in terms of usability, expressivity of the specification languages. So I mentioned signal temporal logic. It's kind of getting popular and adopted and so on, but it still requires some experts in temporal logic to translate some requirements into a proper monitor, proper STL monitor. So there is some work there. Now I wanted to have some more high-level or premature discussions about what they do in modern CPS. And basically the situation there is there's no established tool chain. And there are pieces here and there. There are lots of tools. They're not well plugged together yet. And so the constatation is that the runtime verification here I would say is either not yet or yet another concern. By that I mean, because maybe the agency is more in establishing a good toolchain, that again, what I call toolchain is something that goes from IDs, modeling models to actual code and embedding, and deployment. Okay. And as we had this small discussions, kind of showed, yeah, it's not established. So there's still a lot of work there. So, and as long as you don't have this this established toolchain where you can do this system level kind of monitoring at different stage of the design process, it's a bit early to talk about runtime verification. Well, it's never too early. And it depends what you mean by early. In academia, it's definitely not early. It's the right time. Maybe I'm talking more in the industry. They're not yet. Technology is not yet ready for them to be adapted. Okay, so that's what I mean. Not yet, or yet another, which is because it's a pressing question, which is it's one of the questions to be solved when establishing these toolchains, which is what do we monitor, what do we look at, and how do we integrate this monitoring, etc. And of course, there are lots of fascinating and very challenging questions there, which spans lots of domains. So, biograph, I have some biblio there.